the fifth method of approximation of the integral. So here we have the first condition is n, our number of sub interval has to be even number. So even number of subintervals. Okay, and again, just to recall what we are trying to do, the goal is approximate the definite integral from a to b of f of x dx. Let's not lose sight of what we are trying to do. Okay, so this technique, I think it's the fifth technique, so we write it as 5. And we're going to say it's written like this, 5. S sub n probably won't fit into one line, so delta x divided by 3, not by 4. And here we're going to stick, like we did with the trapezoidal rule, we're going to stick value f of x sub 1, f of x sub 2, f of x sub 3, all the way to f of x sub n, but the coefficient will be different. You know, remember in the trapezoidal rule we had 1, 2, 2, 2, 2, and the last one was back to 1. Here we're going to have 1, 4, 2, 4, 2, 4, 2, 4, and back to 1. Okay, so let's see. It would be 1 multiplying f of x sub 1 plus 4 multiplying f of x sub 2 plus 2 multiplying f of x sub 3 plus 4 multiplying f of x sub 4 plus, and then we do dot dot dot, okay, and then we go to not the one before last, but the one before the one before last, and it will be 2 times f of x sub n minus 2, the one before the one before last, has a coefficient of 2, and then the one before last has coefficient of 4, and the one before last is x sub n minus 1, and finally the last one has coefficient of 1. And then we close the bracket. So the changes are delta x is divided by 3, not by 2, and the coefficient of 1, 4, 2, 4, 2, 4, 2, 4, 1. Why we need an even number? Because here we need an odd number inside. As before, if you have n subintervals, then you end up having n plus 1 terms, because we include both the first term x sub 1 and the last term x sub. So actually, we need to start with a 0 here. Let me think for a second. Yeah, I think we need to start with a 0 here, because the first interval is from 0 to 1. The second interval from 1 to 2. So we need to start with 0, 0, and then go to 1, and then go to 2, and then go to 3. And also, this will be true for this one here. We need to start with 0, 1, 2. The rest is correct. That's how we get the n plus 1 terms. All right. What about the error? One thing we didn't mention, delta x as before, will be b minus a over n, and the error. So the error will be denoted as e sub s for the Simpson, and the error bounds in this case will be k times b minus a to the 5th power divided by 180 n to the 4th. And you can see right off the bat, without addressing k, that you have n to the 4th, which make, and also you have 180. But what about k? Well, k is the highest value of the fourth derivative of the function. Now, you probably ask me how in the world this Simpson rule works. I don't have time to give you a detailed proof for this approximation, but let me give you the principle behind it. Okay, let's go back to the left-hand sum, right-hand sum, and think what we have done. With left-hand sum and right-hand sum, we approximate by connecting 2 points with horizontal line. Remember that we create rectangles. So is the midpoint. But when we come to the trapezoid, we now have a diagonal. With the Simpson, we have a curve connecting, and the curve will be a quadratic curve. So if you look at, for instance, how we approximate the difference between f of x sub I minus 1 and f of x sub I, let's say f of x1 and f of x2, then we'll have a little quadratic in between. So you have a curve on top, not a line, not a horizontal line or a diagonal line as in the trapezoid. And that's why we are looking at the fourth derivative. Go ahead.